a nifty theorem up here on the board. Now, it doesn't have a theorem number because it's not stated as a theorem in your textbook. It's acknowledged as true in your textbook, but they just don't give it a theorem number. Okay. But it says any function built out of continuous functions via arithmetic and or composition is continuous. And the general rule is if you see the word continuous used without any modification, it's understood to mean we're talking continuous on its domain. Okay. So if I build something if I build a function out of functions that are continuous on their domains, I am building a continuous function. I want to just work out an example. Let's let f of xy equal e to the x squared y. Okay. That function looks to me like it's continuous because I'm seeing exponential functions, I'm seeing squaring and multiplication, so it looks continuous. Well, it is. I'm going to formally show you how that is because I can build it out of continuous functions using a combination of arithmetic and composition. Okay. So this is the function that I'm trying to build. Okay. Now we established in the last video that we had two functions. I'm just going to call them g and h. So g of xy equals x and h of xy equals y. Those we established were continuous functions. Okay. Notice these functions are the same type of function as f. They're functions where the input is a point in 2 space and the output is just a single number, because this would give me out just a numeric value as the output. Okay, now I can build the function x squared y by saying that's just g squared times h. Okay. So that's g of xy squared times h of xy. So I built that just using arithmetic. That's multiplication. I multiplied g by itself, because that's what squaring does, and then I multiplied that by h. So therefore I know that that's continuous because I built it out of these continuous functions using arithmetic. Now this is also the same type of function. It's a function where I would plug in a point in 2 space and I would just get out a single number. Okay. Now, I'm going to take a look at k of, we'll just say k of x equals e to the x. X is just a placeholder for my input. Okay. So I'm not saying that this x is necessarily the same as any of the other x's. It's just my usual placeholder for the input. Notice, this is a different sort of function. This is a real valued function of one variable. I'm taking one function, one number, I'm plugging it in, and I'm getting out a number. So this is a different type of function from these other functions. But I can say that f of xy is a composition. Okay, it's just k composed with x squared y. Let me actually just give that a name. I know that was g squared times h. Let's just call that, let's call it capital F of xy. So this is just k of f of xy. Okay. So there I built it out of composition. And we will often see with composition that we're composing different types of functions. I can't actually compose f with g, okay? Because when you do composition, the output from one function becomes the input to the next function. So you can only compose if the type of thing you get for the output of one function is the same sort of thing you're plugging into the other. So, because capital F just gave me out a single number, I can plug in numbers to functions like k that are just real valued functions of one variable. Okay. So there, we've built this as a composition of continuous functions. K was a continuous function of one variable, capital F was a continuous function of 2 variables, and we knew that because we built it out of 2 continuous functions where we used some arithmetic. Okay, now in this case the function that we built has as its domain everything in 2 space. Of course, if in the process of building your functions you introduce restrictions on the domain, that doesn't change this theorem, but the continuity only applies on the domain of the function. So if, for example, I wanted to build another function, we'll just say L of xy equals e to the x squared over y, well, that's continuous on its domain, because I built x squared over y by combining these functions, just using some arithmetic. But because I used division, that introduced some restrictions on the domain. So this would be continuous on its domain. That's not to say it doesn't have some restrictions. It's not continuous if y is 0, simply because it's not defined if y is 0. Okay. So we're pretty much able to tell now, by just looking at functions, if they're going to be continuous, because I could say something like, if I have sine of x plus y squared, that's got to be continuous. I built this out of my component functions using arithmetic. I'm plugging into the sine function, which I know is continuous. So all of the real valued functions we have from first and second semester calculus that we know are continuous, we can use to build continuous functions of 2 and 3 variables. Kind of nice. So that means, for example, if I wanted to take the limit as xy goes to 0, 0 of sine of x plus y squared, this function is continuous on its domain. The origin is in its domain because it's defined everywhere. So this would just be sine of 0 plus 0 squared. That would be sine of 0. That would be 0. So that's the easiest way that we have of evaluating limits if we have a continuous function, and almost all of the functions we're going to be working with will be continuous on their domains. Then if we're evaluating the limit as we approach a point in the domain, we simply evaluate the function at that point. Now, that's not very interesting. So most of the interesting limits are going to be when we evaluate the limit as we approach a point that's not in the domain. And there, we're going to have to take a look at how we actually evaluate those limits. So we'll take a look at that starting in the next video.